Swayam Prabha. Digital India. Educated India.
Welcome to my course non-metallic materials, and this is module number 10, measurement of the mechanical, electrical, thermal, magnetic and optical properties of non-metallic materials, and we are in lecture number 52, thermal analysis technique, particularly differential scanning calorimetry and thermogravimetry. This I will be discussing. So, principle of the differential scanning calorimetry will introduce, and in one of my earlier lectures we already talked about differential thermal analysis as well as TGA. We have introduced the concept, and now in this lecture we will see that what are the factors that affect the DSC or thermogravimetric analysis of a non-metallic materials. What are their typical applications, and what are the principles of thermogravimetric analysis, what are the factors that affect TGA analysis and typical applications of TGA. So, this lecture is devoted to what to do, how to do this measurement, and what informations that you get out of this measurement, and what are the factors that influence your measurement result, and this is a elaboration in this particular lecture. So, differential scaling calorimetry, the basics techniques, the basics of these techniques have already introduced as a part of another lecture. So, the DSC that is used to measure the endothermic and exothermic transition as a function of temperature. So, a range of thermal events that is possible: melting, crystallization, glass transition, curing reactions, decomposition reactions, all these reactions can be identified. And this technique is widely used in case of polymer, pharmaceuticals, organic as well as inorganic compounds, and very small sample size is required, maybe less than 20 milligram, and a wide temperature range is available in the furnace. It can run this measurement starting from minus 120 to 600, and in some instrument it is about 900 degrees Celsius also you can go as a part of the high temperature measurement. So, basic component of the DSC is a temperature controlled furnace with two cells for the sample. One is for the sample, another is one for the inert, and why the inert and is required along with the sample, that already I have described as a part of my earlier lecture. So, DSC measures the difference in the amount of heat in the form of an energy that is required to increase the temperature of the sample and the reference when they are heated and cooled at the same rate. So, both the sample and reference maintained nearly similar type of temperature throughout the experiment. So, it is the measurement of basically the flow of heat. So, if you consider a metal is melting as it is heated. So, before and after the melting transition, solid to liquid transition, it increases the temperature. If you see, it is linearly varies with time. Whenever the melting takes place, the temperature remains almost constant, then again it increases and follow this. So, during melting the temperature is constant and the sample takes heat which is endothermic for this solid to liquid phase transition. So, DSC is a tool to determine the melting temperature. So, in case of DSC the heat flows into either into the sample or out of the sample. So, that heat flow is recorded as a function of temperature or time. So, you are measuring dq by dt. So, you can write dq by d capital T as a function of temperature and the rate of temperature dt by dt. So, dq by dt, that is heat capacity, and heating rate is given by d capital T by d small t. So, this relation is valid in a normal case, and when sample experiences any kind of thermal event, an additional term is introduced. So, it will be Cp and heating rate plus that thermal event, that could be melting, that could be glass transition or various other thermal event. Since the heat flow in DSC is controlled by the heat capacity, it is controlled by the heating rate and also the thermal event that is taking place. So, sample preparation is important. So, thermal transfer is dependent on the thermal conductivity of the sample being investigated. So, they use a small pan where the sample is put. So, if the sample is having lower thermal conductivity, a thermal gradient of course, will be there. So, the surface which will face the furnace part, that will be hot, and this will be in the cooler region. So, in case of a thermal transition, say melting, that can initiate earlier at the sample surface, because the temperature is high and it is less thermally conductive, and core may not be seeing the transition. So, ideally DSC sample should be a thin circular disc, not a massive one. So, that this thermal gradient is avoided. Now, you can think of that the parameter like sensitivity, resolution of the measurement, transition peak, etc., how they are dependent on the sample size. So, first let us talk about the sensitivity. So, the heat difference between the sample and inert is large for larger sample. So, of course, it will increase. So, sample size if it is increases, the sensitivity will increase, but at the same time resolution will decrease in the sample because particularly if it is having lower thermal conductivity, then resolution certainly will decrease, because this part will not get melted as compared to the surface having a large sample size. Peak temperature onset will not be affected, but the peak temperature will increase with the increase in sample size, because it will take time to melt the whole of it. So, for larger sample size, sensitivity will increase, resolution will decrease, and transition peak will increase to a higher temperature. And same thing will happen if you decrease it, then sensitivity will also decrease, resolution will increase, and for a decreased sample size, your transition peak temperature will be correctly predicted. Heating rate is also affect the correctness of the measurement. So, lower heating rate is about 5 degrees Celsius per minute. So, sample is heated homogeneously, and there is negligible thermal gradient. In case of heating rate, if it is high, then there is thermal gradient. So, sample to follow the fast heating rate is problematic. So, the phase transition is usually shift to high temperature. Onset of melting will be less affected. For the sample which are poorer in thermal conductivity, having poor thermal conductivity, lower heating rate is always recommended. So, it is a typical example for a particular metal, and this metal indium is used as one of the standard for DSC calibration. You can see the heating rate is increased 2, 5, 10 and 20. Onset temperature, it remains more or less constant. Peak temperature, it varies. You see that almost with the heating rate there is a 1 degree difference, it takes place. And the heat flow, they are normally not vary that much. So, a lower heating rate results a higher resolution and very good reproducibility, and this should be used for samples which are poor thermal conductivity and lower thermal transition. At lower heating rate, the sensitivity as you can see is low, and the experimental time of course is longer. It takes long time to complete the experiment. So, usually a intermediate heating is preferred, which is typically 20 degree Celsius per minute, which gives you a reasonable good sensitivity. Resolution is also good, experimental time requirement is not that high. So, depending on the type of sample, you may have to choose the right kind of heating rate. Now, in case of DSC, the thermal history is important, particularly in case of a semi-crystalline sample, which is prepared originally under various other condition. So, the crystallinity may be different, it may have different types of crystals. So, the DSC that will be dependent on the initial crystallinity of that polymer sample, if it is a semi-crystalline polymer. So, for effective comparison, the thermal history should be removed. So, initially the sample is heated and then again cooled back. So, a heating and cooling cycle is required. So, usually heating is done beyond the melting temperature, and then the sample is soaked for 5 to 10 minutes and then cooled rapidly at room temperature, so that it achieve a amorphous state. So, it is now known that the sample is originally in amorphous state and it does not have any prehistory for partial crystallinity. Then you do the second heating and measure the DSC characteristics. So, for polymeric sample it works, but not for all samples this criteria will work. For example, if you take a partially cured resin, so heating and cooling and again reheating method, that cannot be applied here to remove the thermal history, because it is partially cured. A chemical reaction has been taking place in the sample to form a permanent chemical change, and that is not thermally reversible. So, depending on the sample, the thermal history is important for you to know before performing a DSC measurement. Usually inert ambient is used in case of DSC. Nitrogen is a preferable gas because it increases the sensitivity and it is a poor thermal conductor. Sometimes helium also can be used, because helium is having a higher thermal conductivity than nitrogen, but helium is expensive, but it increases the resolution of the thermal transition. Very accurately thermal transition you can achieve by using helium. When decomposition reaction is taking place, then one can use air when you want to know the thermal degradation of organic materials. Then the air ambient is used. Temperature calibration is required. Sample temperature, as you can understand, that is slightly lowered than the furnace temperature. So, for accurate measurement of any transition temperature, you need to have a temperature calibration, and for this purpose the standard are used, which has very well known heat capacity and transition temperature. Usually metals are used, indium, tin, lead, that is used as standard. They have a very sharp, in fact, I have shown you the melting transition of indium metal. It is very sharp temperature, melting temperature is there at relatively low melting temperature, at low temperature it melts. So, at least in the whole temperature regime where the experiment is done, at least 2 temperature point should be calibrated to know exactly the temperature of the equipment, what instrument, whatever it is, whatever it is showing, it is correct. And heating rate should not change the transition temperature of the standard. So, that you have seen that even if you change the heating rate, the transition temperature of a standard metal indium, that do not change much. So, here we can show one example, a thermal event of a polymer. So, as you can see, melting is an endothermic reaction, and this is a first order transition, and this melting point that strongly depends on the heating rate, because they have a distribution of the crystallite in the polymer sample, and each of them have different melting temperature. So, usually this transition in broad in nature, and with heating rate the melting point shifts to higher temperature with the increase of the heating rate. Crystallization, as you know that the crystallization that basically will depend on the nucleation, and from the melting, if you cool it down, it depends on the undercooling. Undercooling, this crystallization will be dependent on. So, we can define the value of alpha, which is the degree of crystallinity, and you can measure the value of del H c, which is the enthalpy of crystallization, and which is nothing but the area under the peak. And if you know the crystallization enthalpy for a fully crystalline sample, then one can calculate the value of alpha. And crystallization of a polymer is a kinetic process, and certainly it will depend on the cooling rate. Faster cooling rate, usually the polymer chain will have shorter time to arrange in a ordered structure. So, it will be amorphous in nature. So, typically from the exothermic peak corresponding to this crystallization, this onset temperature is the nucleation temperature, and this temperature, if you have a tangent here, and this is your end temperature. So, this will be determined by both melting and crystallization of a semicrystalline polymer that can be identified by ADSC measurement. Apart from that, you have a small deviation, which is the indication of a glass transition temperature. So, the figure here, it shows the glass transition is eventually, if you consider the elastic modulus versus temperature plot of a polymer, then initially this is a glassy region where elastic modulus remain constant, and then there is a glass to rubbery region. This is called a glass transition region. It is having a plateau also, and followed by this melting transition. So, usually the elastic modulus changes when the polymer is heated, and you can also get the same information by measuring its elastic modulus. So, glass transition is a critical temperature which separates the glassy region with rubbery behavior. So, at Tg, amorphous polymer, they becomes brittle on cooling and soft on heating. So, if you go to this side, then it is brittle in nature. You go to this side, then it is a rubbery region. So, glass transition usually takes place over a broad region because mainly of the polydispersity of polymer chain, and it is a second order transition. And Tg actually depends on the heating rate. If the heating rate is increased, then the glass transition temperature is also increased. So, this is in DSC, it is just a small kind of variation like this. So, onset temperature can be identified, and also this temperature can be identified. So, in between, in fact, if you differentiate this plot, this in between temperature, that is taken as the exact Tg of the polymer that is being experimented. TGA, thermogravimetric analysis, that uses a balance. So, specimen is placed on a pan, the other side of the balance holds additional weight to offset the mass change because of the reaction that might have taken place in the sample during heating. The balance operates in a null balance principle. A 0 position, equal amount of light shines on two photodiodes, and if the balance move out of the null position, an unequal amount of light shines these two photodiode. So, a current is applied to the meter, so that the movement return to the balance to the null position. So, amount of this applied current is in fact proportional to the weight loss and weight gain. So, that is the principle that is followed in commercial thermogravimetric instrument. So, sample preparation, either you can use a powder sample or a very smallest cut sample if it is difficult to make a powder. Weight is typically taken 10 to 20 milligram. The surface area should be as high as possible. It should be maximized to improve the weight loss resolution. So, for most of this TGA, you have a baseline drift, which is typically plus minus 0.025 milligram. So, if you have a 10 milligram sample, it is 0.25%. If you increase it 20 milligram sample, this is 0.125%. So, larger sample will help in terms of the baseline, but the sample weight and volume should not be too large. So, the factors that affect a typical TG curve, which is shown here, which is a weight loss as a function of temperature. So, sample holder is important, sample mass is important, heating rate is important, and also the sample furnace temperature is important. So, the geometry and size, heat sink properties of the sample holder affects the heat transfer to the center of the sample where inside the crucible. So, true thermal degradation behavior is achieved using a very thin aluminum pan. Using a heavy pan, that might overestimate the degradation temperature. Sample mass, as I told, that larger the sample mass, greater is the deviation of temperature because of the endothermic or exothermic reaction taking place. So, the deviation of temperature will be more. So, thermal mass actually takes a long time for a larger sample for temperature stabilization. If you take a large sample weight that is undergoing a decomposition reaction, so it will take long time for the gases to come out of the sample. So, degradation temperature, in fact, they will be estimated higher because the weight loss will simultaneously be taking place. So, it will be higher in case of larger sample. And of course, during thermal gradient, due to the thermal gradient, sample particularly those samples which are having poor thermal conductivity, for larger mass, slower degradation will be observed. In the temperature range, if you consider 25 to 325 degree Celsius, a heating rate 1 degree Celsius per minute, measuring time is 300 minute. If you change the heating rate to 20 degree Celsius per minute, measuring time is only 15 minutes. So, at higher heating rate the sample degradation will be less as compared to one with slower heating rate, because the degradation temperature at higher heating rate that will be estimated larger, because the sample is seeing very small time the temperature change. So, that affects the degradation temperature. Furnace atmosphere is also important, and as you can see that the same sample when you are doing the measurement in air ambient, it depends on the type of degradation in the sample. So, nature of degradation product, that is important. So, in case of air the degradation is expedite, it occurs at relatively lower temperature as compared to the same in nitrogen. Also the degradation behavior in nitrogen is very different as compared to that of in air. So, the type of degradation, it is important, and therefore, the furnace atmosphere will also have to be judiciously selected. Thermal stability can be determined by TGA analysis. The onset for the thermal degradation of the polymer material, that can be determined by TGA, as you can see here for PVC, for PMMA, HDPE, PTFE and PI. Progressively the thermal degradation temperature, you can see the onset of the wet loss that is taking place. It is done in nitrogen ambient. So, this is a good way to check the thermal stability of the sample. Another thing what is done by TGA is composition analysis. So, here typically we have say mixed silicon dioxide with carbon black with a polymer, and it is absorbing about 1% of moisture, and due to thermogravimetric analysis you get the wet loss, and eventually from the wet loss you can get the composition of the mixture. So, it can be seen that it consists of 1% of moisture, about 39% polymer it decomposes, then 36% of carbon, and whatever is remaining about 24% that is the silica. So, each component they usually show its own plateau, and the percentage can be directly read. So, this is very useful for the slurry preparation, for example, for battery, rechargeable battery, we prepare the slurry to coat the electrode material, current collectors. So, the composition of the slurry that can be identified by thermogravimetric analysis. Oxidative stability also can be identified by the TGA. So, here is one example, a polymer with a flame retardant and without a flame retardant. So, a flammable material can be modified by adding a flame retardant. So, this retardant resists the spread of the fire. So, this figure shows the flame retardant improve the thermal stability of an epoxy polymer, because its degradation temperature is expedite, is moved to high temperature about 150 degrees Celsius. So, that is the usefulness of thermogravimetric analysis. So, this part the study material is from the book by Zhang, Li and Kumar, chapter number 10, macro and micro thermal analysis, and apart from that the book by Gabbert and Wunderlich, that is also helpful for clarifying some of the idea taught in this lecture. So, in this lecture we have mainly focused on differential scaling calorimetry, talked about the effect of sample size and sample preparation, effect of heating rate, thermal history, effect of atmosphere, temperature calibration, and finally, how and what are the stages and how this DSC can be used as a material characterization tool. Next, we took thermogravimetric analysis. First, we identified the principle of operation, then sample preparation, factors affecting the thermogravimetric curve, and then we cited some typical applications. Thank you for your attention.